So this week we are going to finish on our discussions on differential amplifiers. And also we'll take a look at how do we design op amps. So for example, by now you're kind of getting an intuitive sense that, okay, why we are learning all these things, that why did we learn about MOSFETs, why did we learn about amplifiers, followed by differential amplifiers, that eventually we want to build an op amp. We started with an op amp in this course. We want to build an op amp as we get to the final few lectures of this course. So how do we do that? That's what we are going to learn in today's lecture and next lecture, which is on Wednesday, basically. So along with that, I have also uploaded your homework 8 and homework 9. Although these two homeworks will be due after Thanksgiving break, homework 8 will be the op-amp design. I've also uploaded an op-amp design example, which should help you in solving that homework 8. Of course, we will go through that homework design or the op-amp design example in the class as well. And then homework 9 will be on CMOS logic circuits, on which you are already going through the lab 7. Also, as you try to solve the problems given in lab 7, please look at this video from last year, and also the write-up, or basically the notes, are also uploaded on Canvas. So although we haven't yet covered it now, but we'll try to cover it, let's say, by the end of this week or so. But please look at this video if you are having the lab 7 this week. All right, so differential amplifiers. We already know that the job of a differential amplifier is to amplify a differential input. And a differential input will mean that, okay, if you have a positive half cycle of the sine wave first and a negative half cycle later for V1, V2 will be 180-degree shifted version of that. And you have also looked into two different approaches to find out the gain of a differential amplifier. One based on superposition principle, that you consider V1 and V2 separately and do the analysis. And the second principle was to consider the half circuit of the differential amplifier. So basically, what is going to be the AC equivalent half circuit? Because this tail current source, if this is an ideal current source, looking here, you'll see infinite impedance. Also, we have seen that if V1 is this positive half cycle first and then this negative half cycle, and V2 is exactly opposite of that, if you consider this point VP, the voltage at VP will be a linear superposition of the source followed voltage of V1, because if V1 is applied at the gate, at the source, you know that if your output is at the source, your input is at the gate, that configuration is called a source follower. And for a source follower in the ideal scenario, the gain is exactly equal to 1. So you'll have V1, the exact representation of V1 available at this node P or VP, if you're considering only V1. On the other hand, if you're considering only V2, this sine wave also manifests itself at the same node VP. So you get a linear superposition of those two sine waves, which means you have no sine wave at all in node VP. And that is the reason why we said that this point is an AC ground. The point VP, that's an AC ground. And what that means is that the two halves of the differential amplifier, that is this half circuit and that half circuit, both of them terminate at the AC ground at node P. You don't even need to consider the tail current source. And that makes your analysis very simple, that you just have an input to a common source amplifier. Why we are calling it a common source? Because your input is at the gate terminal for transistor over here, and the source terminal is grounded, which is the common terminal. So we call it a common source amplifier, which is the half circuit of the differential amplifier. And for the common source amplifier, you already know what would be the gain equation. So we saw all of that in the last lecture. And we also saw the definition of the differential mode gain, the common mode gain. The ratio of those two is going to be called the common mode rejection ratio. And ideally, for an op amp, the common mode rejection ratio should be infinitely large. That means the differential mode gain needs to be very large, whereas the common mode gain needs to be very small. One thing just keep in mind, whenever we are talking about common mode gain, we are still talking about AC signals. So we are talking about applying an AC signal at the two gates V1 and V2 when we talk about common mode signals. Okay, so now today, let's take a look at a little bit more complex scenarios with differential amplifiers. So instead of instead of connecting a resistor as the load, so over here in the earlier picture, if I go back over here, you had a resistance as the load. And then you had your input applied at the two NMOSes over here, and you had a tail current source. Now, all we are saying is that instead of the resistor, you'll replace that with a MOSFET based load. And this is something, again, you have looked into before when you were looking into single stage MOSFETs or single ended MOSFETs. That if we replace the resistance with a MOSFET, it will depend on the resistance that we'll see in that scenario will depend on how much resistance do you see looking into this particular terminal and how much resistance you see looking into this particular terminal. So this is your output terminal, Vout1. So from Vout1 looking up, you see a diode connected transistor M3. See, this transistor M3 is diode connected because the drain and the gate are connected together. And we have already seen that for a diode connected transistor, the resistance that you see looking into the drain terminal is going to be 1 upon GM. For the diode connected transistor, the resistance looking into the drain is going to be 1 upon GM. The resistance looking into the source of a transistor is anyway 1 upon GM. Right? That's always the case. When we are trying to take a look at the resistance looking into the drain, only for diode connected transistors it's 1 upon GM. In all other cases, it is RO. That's what we have seen before. Okay. So the resistance looking up is 1 upon GM at the output terminal Vout1. Resistance looking down is the drain of this transistor M1. And of course, M1 is not diode connected, which means that the resistance looking into the drain, you'll see RO. So in that case, you're basically representing the resistance in up, looking upwards. That resistance becomes 1 upon GM3 because this is transistor M3. So you have 1 upon GM3 in parallel with RO1. So if you take a look at the resistance looking down at the same output terminal, you'll see RO1, the RO of transistor M1. So 1 upon GM3 in parallel with RO1, that's going to be the overall resistance that you'll see at the output terminal. Again, nothing fancy, nothing new here. Everything has been learned when we were discussing single-ended amplifiers. So that's the resistance at this output terminal Vout1. What is the GM of the transistor that we are interested in? Because V1 is applied at the transistor M1, you are interested in the GM of transistor M1. So you have GM of transistor M1 multiplied with whatever output resistance you have for the amplifier. And you know GM multiplied with Rout is your voltage gain. Now, if your 1 upon GM3 is much, much smaller than RO1, which is likely to be the case, that's generally the values of GM and RO, as you have seen while solving the homework problems, that 1 upon GM is generally much, much smaller than RO. So 1 upon GM3 in parallel with RO1, that will effectively become 1 upon GM3. So you have your gain as the ratio of the two GMs, GM1 divided by GM3. Of course, it's negative because it's a common source amplifier as the half circuit. Of course, that will also be equal to minus of GM2 over GM4 if you consider the right-hand side half circuit. All right. You also know that because this is the ratio of GMs, eventually it will become a ratio of W over L of the transistor. And if the lengths are same, it will eventually become a ratio of Ws or the widths of the transistors. And you cannot really have an extremely large width along with an extremely small width for the transistors M1 and M3. So they will always be in the same ballpark range. Maybe you can make one of them 10 times larger or 20 times larger than the other, but you cannot really make one, let's say, 1,000 times larger than the other. That's like physically going to be impossible because one transistor would be so big and the other transistor will be so small that we'll be having trouble connecting the two together. Yeah. Think of it that one transistor in your breadboard is 1,000 times larger than the other transistor on your breadboard, right? How does that look like? And how much difficult it becomes to connect the proper nodes together. And of course, there would be effect of parasitics and so on. And that is the reason why whenever you have the ratio of two GMs, the gain cannot be much because the widths of the transistors cannot differ by much as compared to each other. So this particular configuration may have a gain of maybe 5 or 7, but it can never have a gain of 100. Now, for your op-amp, ideally, what is the gain of an op-amp? For an ideal op-amp? Infinity. So we are still not achieving infinity. You have a differential stage. So you know that for an op-amp, you have a differential input because the definition of the op-amp tells you that if the differential input between these two, let's say V plus and V minus, And if the gain of the op-amp is A, then the output of the op-amp will be A multiplied with V plus minus V minus. So the op-amp basically operates in a differential mode, that whatever is the difference of the two inputs, multiply that with the gain of the op-amp, you'll get the output. That's the definition of an op-amp and the gain of the op-amp. And of course, you should see infinite impedance looking into the input terminals of the op-amp, looking here as well as looking here. So if you think of the input stage, whatever is there inside the op-amp, as this diff amp with diode connected load. Of course, you'll see infinite impedance specifically at DC or low frequencies, because looking into the gate terminals, you'll see infinite impedance. You will multiply the input difference and then multiply that with the gain of the circuit, you'll get the output. However, there are two big differences here. Right? First difference is that the gain of the op-amp is not infinity, it is small. Maybe it is 5, maybe it is 10, but definitely not infinity. The second difference is that for the op-amp, whenever you had drawn an op-amp earlier, you always had two inputs and one output. We still don't have that. We have two inputs and two outputs in the differential amplifier circuit. So how do we eventually get to a scenario where our circuit or the overall configuration looks similar to an op-amp, and we'll all, of course, try to have infinite gain at some point and so on. Okay. All right. So the first problem is that we do not have infinite gain. So how do we increase gain? Again, something that you had learned when we were discussing single-ended op-amps or single-ended amplifiers, that if you want to have a diff amp with current source load, that instead of diode connecting these loads or M3 and M4 transistors, if you make them as a current source, so you bias those transistors in a way, so you apply this VBP, the voltage bias at the gate terminal, or you can bias it using current meters. You have already learned current meters, you have solved your homework 7, and you know that you could have also biased it using something like this. So for example, let's say I have a current source, and then I have a PMOS over here. I diode connect one end of this PMOS and then connect the gates of the two PMOSs together. So whatever current I have flowing in this branch would be the same current flowing in this branch if your M3 transistor and let's say this transistor is M0, if their W over L ratios are same. So you can bias them using currents as well, or you could be biasing them using voltages. It's up to you. Generally, current biasing is much more stable because currents are less affected by noise in a circuit, whereas voltage gets affected by noise or voltage drop and so on. But that's one way of doing the biasing. So if you assume that you are doing the biasing for M3 and M4 transistor, in that case, you do not have the diode-connected transistors M3 and M4 anymore. So looking up from the output terminal at this Vout1 terminal, looking up, you'll see drain of the M3 transistor. That means you'll see RO3. Looking down, you'll see drain of the M1 transistor. That means you'll see RO1. So the effective output resistance now becomes RO1 in parallel with RO3 instead of RO1 in parallel with 1 upon GM3, which was the previous scenario. Okay. So just by going from a diode-connected load to a current source-based load, you increase your output resistance, and that means you'll eventually increase your gain. Because gain is just GM1, which is the GM of this transistor, which can stay the same, multiplied with a higher RO. That means your AV or the voltage gain is going to be higher. So in this case, the gain will be more as compared to the scenario with the diode connected load. However, there is still a problem. Like will not go, or I'd like to define the problem here, but the solution is generally given in your analog circuits on graduate level courses. We'll also take a look at the solution a little bit, but then I'm not going to go into the discussion of the solution too much. So what is the problem that we have? So as we just said, that you are going to create, let's say, a biasing through some sort of, let's say, current mirror. You'll have some current flowing in this branch. You'll mirror this current, and then you'll provide that at the gate. Maybe you'll provide the same voltage, or you'll connect the same point at the gate over here as well, right? Because eventually you want the same current to flow in the left side branch as well as the right side branch. And those two currents are supposed to get added up and then flow through the tail current source, right? So these two currents are supposed to get added up and flow through the tail current source. Now, the problem that is present in this circuit is that you have a tail current source. The tail current source wants a particular amount of current to flow through the entire circuit. Half of that flows to left side branch, half of that flows to right side branch. On the other hand, there is another current source over here on the left that tries to mirror whatever current is there over here, that tries to mirror the same current in the branches M3 and M4. So there is going to be a fight between the current sources, the current source that is present over here and the current source that is present over here. So these two current sources will fight each other. Now you can say, okay, ideally I can have the same value of the current, right? I can make sure that this current source's value is half of the tail current source's value. So whatever I mirror at M3 and M4 transistor, that's going to be half of my tail current source's value. Fine, you can do that. But in a real scenario, the transistors are not ideal. You'll not get the exact same ratio of mirroring. And in that case, the current sources will still fight each other. Because it's never possible to have the left side, this current source, exactly as half of that tail current source. It's practically never possible. Ideally, for solving problems, always possible. But in a practical circuit, that is never possible. So this is a problem. And I want this class to be more about practical circuits and the problems in practical circuits. So that's why I wanted to introduce the concept. However, the solution is much more complex. The solution is generally taught in graduate level courses. The solution is called common mode feedback. So I'm not going to talk about details on common mode feedback, but just know that this exists, that, okay, there could always be a fight between those two current sources. One current source defined by your M3 and M4 transistor. The other current source is basically your tail transistor. To stop the fighting between the two transistors, the way it is done is use whatever current source, use only one current source. Do not use two current sources. That's the solution, right? The solution is as simple as that do not use two current sources, use only one current source and derive the second current source using the first. Now, how do you do that? The entire design of the circuit is complex. That's why I said that we are not going to show that. But the idea is very simple. What is the idea is, let this current ISS, this tail current source, define whatever current it wants to make flow through this left side and right side branch. Of course, that is going to be half of the tail current source, because half of the current flows on the right side branch, half of that flows in the left side branch. Now that current will create a certain amount of voltage at or DC voltage at the two output terminals. What are our output terminals? The output terminals are this one, let's say that's Vout1, and this one, which is Vout2. So of course, there would be an AC at the output terminals, but at the same time, there would be a DC on the output terminals, right? If you set your DC at that output terminal to a voltage that you want, right? So you can always set that voltage to something that you want that voltage to be, that DC voltage to be, and that can be done using this common mode feedback circuitry. So what we basically do is that take an average of these two voltage values, and that averaging is done through this RC circuit, this RC low-pass filtering. Again, that's why I'm saying that, okay, what is going to be the mathematical formulation of that? We are not going into the details of this. What you're eventually doing is that you're taking the average of these two DC voltage values, and you want to have a desired Vout CM, a Vout common mode DC voltage at these two output terminals. So that you're putting in as the input of another op-amp. Now you might ask, okay, I haven't built my first op-amp yet. How do I build my second op-amp, which is over here? And that's why I'm saying that, yeah, we don't need to worry about that right now. It will be taught in your graduate classes. But let's say you have an op-amp. Just assume that you have an op-amp. And then the output of the op-amp is provided as these bias voltages. So what it will do is that even if there is a small amount of shift in the DC voltages at these two output terminals, the op-amp will try to make sure, op-amp has an infinite gain. That means it will try to make sure that the difference at its input is very close to zero. So if you have a desired Vout CM, that same Vout CM will be eventually, like through this loop, because we have this feedback loop, the negative feedback will ensure that at the other terminal of the op-amp as well, you will have the same Vout CM voltage, which means that these two voltages, the drain voltages of M3 and M4 transistor, they will be fixed. The source voltage of M3 and M4 transistor is fixed. The gate voltage will become the output of the op-amp, and that will make sure that the current through M3 and M4 are always fixed, and that is half of this ISS transistor's current. So through this feedback loop, you can achieve that, but it's something that I just wanted to introduce to you, but will not go into the details of the calculation of how that is achieved. Okay. Now, yeah, question.
Was that like an arbitrary decision, or could you have these NMOS also, or is like do we need?
Right. That's a great question. So generally, you have seen that if you have PMOSes over here, so you know that current is flowing from top to bottom, right? So the source terminal of the PMOS can always be connected to this VDD, which is a good thing to do, because then the source and the body terminal of the PMOS gets connected to VDD, and you know that if I draw the PMOS structure over here, this is P, and this is my gate, and this is the body. The body of the PMOS, let's say, connected to VDD. The source of the PMOS is connected to VDD. So this is the source, and this is the drain of the PMOS, which is at a lower potential than VDD. That means the PN junction diode, that this in the body of the PMOS is always an N-type semiconductor. The PN junction diode are either zero biased or reverse biased. That means there is no additional power loss because of those diodes getting turned on. Right? On the other hand, if you and that is the reason why you would like to connect the source of the PMOS to VDD and the source of the NMOS to ground. That is also a reason why in any circuit, the top portion is designed using PMOS and the bottom portion is designed using NMOS. Right? Your output is generally in the middle, but you are able to connect the source and the body of the PMOS to VDD, whereas the source and the body of the NMOS to ground, keeping those leakage currents at a minimum. So you can do that. Also, we'll learn about another reason when we start discussing about CMOS circuits, CMOS digital circuits. We'll learn about that reason as well, but this is something that you can, at this point, this is one of the reasons why we keep PMOS on top and NMOS at the bottom. If you had put NMOS on top, the problem would have been there would be two NMOSes stacked. Why did you connect the NMOS's body to? Right? Which source? Like you want to connect the source and the body together. But the source of one NMOS will be this midpoint. The source of the other NMOS will be over here. Why would you connect the body of the two NMOSes? Like those two are different points, right? Okay. Defamp with current mirror load. Now, instead of having a current source on top, which of course creates the problem with CMFB, that there would be a fight between these two current sources, and you need a common mode feedback to basically make sure that you generate one current source from the other. But there is another simpler solution to it. And this is something you have also learned over the last few lectures, that I can create a current mirror-like structure on the top. Okay? If I create a current mirror-like structure on the top, then whatever current is flowing in this branch, I'm mirroring that current on the right side branch, right? That's what I wanted to do anyway. That I want to mirror the current on the left side branch to the current on the right side branch. In that case, I will not need those external current sources to bias M3 and M4. M3 is biased automatically because this is a diode connected configuration, which means that M3 will always be in saturation. We know that the diode connected transistors are always in saturation because gate and drain are connected together. So VGS is equal to VDS, which is always going to be higher than V overdrive, which is VGS minus VT. So M3 transistor is always in saturation. And since you're mirroring the same current with the same size transistor, M4 is also going to be in saturation. Now, in this case, interestingly, the output, if you take the output from this terminal, the right side terminal only, the right side output terminal, that is going to be your Vout1 minus Vout2 in the previous scenario. And I'll tell you why. We'll discuss that, why that is the case. So in the previous scenarios, you had a Vout1 on the left side branch. You had a Vout1 on left side branch and you had a Vout2 on the right side branch. Of course, your output is Vout1 minus Vout2. That's the differential output. By doing the current mirror load, by having the current mirror load, you automatically do the subtraction, and I'll prove that. It's not that you don't have to take my word for granted. We'll prove that your output voltage is going to be the subtraction of the original Vout1 minus Vout2 that you had seen in the previous slide, which is going to be the differential mode gain multiplied with V1 minus V2. So this is also called a differential to single-ended converter or a differential to single-ended amplifier, because you have two inputs, V1 and V2, but you have only one output. And that one output actually takes care of the subtraction at the two original outputs of the op-amp. Now this looks very similar to an op-amp, but of course this is still not an op-amp because of multiple reasons, which we'll talk later. One big reason is that, of course, it does not have infinite gain. But in this case, the voltage gain is going to be GM1 multiplied with RO2 in parallel with RO4. So GM1, let's say the gain of this, the GM of this transistor or the GM of this transistor, because M1 and M2, they are identical transistors. So you can write the gain as GM1 or GM2 multiplied with the resistance at the output terminal. What is the resistance at the output terminal? Here, looking up at the drain of M4, you see RO4. Looking down at the drain of M2, you'll see RO2. So at the output terminal, you have RO2 in parallel with RO4. That's the output resistance. That multiplied with the input transistor's GM, that will give you the overall voltage gain. Now, something that we still need to prove is that this configuration automatically gives you the subtraction at the output for the original differential amplifier. That is something we have not proven. So let's do that first. So you can always prove that using small signal analysis, that you can draw the small signal model of these transistors. I leave that out as an exercise. Should be a good exercise of solving problems using small signal analysis, because we have looked into a lot of small signal analysis in the class. And whenever you're trying to find out the gain of any circuit, if you don't remember, let's say, all these formulas, the best way to solve the problem is always to go for or resort to small signal analysis. Right? Small signal analysis can never be wrong. So if you're not sure, do the small signal analysis. It will take a little bit more time, but as you practice more and more, you'll get faster at it. So we'll take a look at an intuitive approach. Now, the intuitive approach will start making more and more sense if you become better and better at small signal analysis. That's why I said practice as much as you can for the end-term exam as well. Practice more small signal analysis related problems. I'll post a few problems before our Thanksgiving break so that you can practice. But eventually you'll see that as you practice more, you'll build an intuition of, okay, how do these different kinds of circuits behave? And I'm going to talk about that intuitive behavior or intuitively how we can solve this. And for many of you, the intuitive analysis will make a lot of sense. If it doesn't make a lot of sense, I'll suggest that try to solve as many small signal models as you can, and then gradually the intuitive models will also start making more and more sense. Okay, so the intuitive approach over here, what we are going to say is that, first of all, this is a current mirror, right? All of us agree on that this is a current mirror, because you're mirroring, or you have this direct connected transistor on one side, and you're connecting the gates of the two transistors together. And you have solved problems in homework 7 related to this. So you know that this is a current mirror, which means that whatever current flows on the left side should also flow on the right side branch, right? Now, if you are considering only Vin1 for a differential amplifier, of course, you'll have Vin1 and Vin2 as well. So you're going to have Vin1 and Vin2. But for a moment, let's just say that we have only Vin1. So we're doing a superposition principle, right? We're considering only the Vin1 first, and then we'll consider Vin2 later. Now, if there is a current flowing on the left side transistor M3 and that transistor is GM1 times V1, why am I saying that this is GM1 times V1? Because my input applied voltage is V1. The transistor has a transconductance of GM1. So it will force a AC current GM1 times V1 on the left side branch. And that AC current will be flowing through this M3 transistor. Because M3 and M4 are mirror connected, M3 and M4 are mirror connected, the same current will flow through M4 as well. So GM1 times V1 will also flow through M4. All right. Now, remember that if we are trying to find out the effective GM, we already did that when we were looking at single-ended amplifiers, that we want to find out effective GM in a circuit and we want to find out effective R out in a circuit. Multiply the two, you get GM times R out, which is the gain of the circuit, right? That's something we have learned in single-ended amplifiers as well. Now, how do you find out effective GM in a circuit? That's basically you want to find out what is the output current as a function of your input voltage, and output current divided by input voltage becomes your effective GM, because GM is defined in that way. It's transconductance. The transfer function is a conductance, which means output is current, input is voltage. Now, if you say that my output is current, again, this is something we looked at when we are solving the single-ended scenario, but I'll repeat that once again, that I have a black box, and that black box is my Norton equivalent circuit. Why is it the Norton equivalent circuit? Because I want to find out the output current. For a Thevenin equivalent circuit, the output terminals are open. So there is no current flowing in the output for the Thevenin equivalent. But if we want to find out the current, you short those two. You short the two terminals at the output, find out what is the current flowing at the output. So that's the Norton equivalence of the same thing, right? So if you want to find out GM, that as a function of my input voltage, how much current am I getting at the output? So you short your output terminals. That's what you do for Norton equivalent. So if we are trying to find out the effective GM in this case as well, for the differential amplified with current mirrored load, I am going to connect my output terminal, which is basically this terminal, to the other terminal, which is the ground, right? But I want to short my output terminal with ground, because this is always ground. The lower terminal is always ground. You're just connecting the top terminal with the bottom one. So I am going to connect this terminal to ground if I'm trying to find out the effective GM of the circuit. So in that case, I already had this GM1 times V1 flowing through M3. That current will be mirrored. So through M4, I have GM1 times V1. That's the current that is flowing here. Okay. At the same time, if I apply a V2, if I apply the second voltage on transistor M2, if I am applying V2, I will get a current that is flowing like that. And that current is going to be this minus GM2 times V2. Why this is minus? Because one current is going into the ground, the other current is coming out of the ground and flowing through this. Right? These are AC currents. That's why the current can come out of the ground. So you have GM1 times V1 minus GM2 times V2. That's the overall current that you have at the right side branch. Even though on the left side branch, you just have GM1 times V1 as the AC current. So the output node's current is GM1 times V1 minus V2. Now remember, V1 minus V2 is basically your input differential voltage. So your output node current is GM1 times that input differential voltage. So you already have created a current at the output terminal, which is GM times the input differential voltage. All you need to do now is multiply a resistance with this current. If I multiply R out with the output node current, I get the output node's voltage. Right? What is the output node R out? Looking up, you see drain of M4. Looking down, you see drain of M2. So you have RO4 parallel with RO2. That's your R out. So RO4 in parallel with RO2. That's my R out. And when I multiply this R out with the output node current, which is GM1 times V1 minus V2, I get my output node voltage. So if I want to find out my gain, I'll divide my output node voltage with my input node voltage. And my input node voltage, differential voltage was V1 minus V2. And that means what is my gain? My gain is going to be GM1 times RO4 in parallel with RO2. So GM1 times RO4 in parallel with RO2, that gives me my gain. And that's what we said, that the gain of this circuit is going to be, if I go back a little bit, the gain, voltage gain of this circuit is going to be minus of GM1 times RO2 parallel RO4. So we proved the gain. We also proved the fact that you already have a subtraction of those AC currents. You already have the subtraction of the AC currents, GM1 times V1 minus GM2 times V2 at that output branch by doing this current mirroring, which was not possible earlier. Earlier, we always had to take the difference of two output voltages. So we always had two output terminals. Now I can have only one output terminal. So now this is going to be very close to how an op-amp looks like. I have two input voltages, V1, V2. I have infinite input impedance. I have one output voltage. But the problem is that I still don't have infinite gain. And there is another problem that I'm going to talk about right after this. So this is still not an op-amp. Why? Op-amp properties, infinite input impedance, you have infinite gain. You can design it for a high gain, yes. And you can just maybe cascade number of stages and you can multiply the gain. Let's say one amplifier gives you a gain of 10 and you have 10 of them, right? So 10 multiplied with 10, multiplied with 10, multiplied with 10, and so on. So 10 to the power 10 becomes your overall gain if you have 10 stages cascaded with each other. So you can have infinite gain if you are cascading number of stages. What is the other property of an op-amp? Zero output impedance. Do we have zero output impedance? And that answer is a resounding no, because the output impedance in this case is the output impedance at the output terminal. And at the output terminal, looking up, you see RO4, looking down, you see RO2. Your overall output impedance is RO2 parallel with RO4. Now, RO2 could be 100 kilo ohm, RO4 could be another 100 kilo ohm. Parallel combination of those two, 50 kilo ohm. It's not zero. Right? So my output impedance is not zero. That's one problem that we have identified, right? So this is still a no. So we need low output impedance and we need more gain to convert this to an op-amp. So I can make a few different choices. So for example, let's say, by the way, I already know the solutions though. And even though this is not an op-amp yet, but we know how to make it an op-amp. You already know that for a source follower or a common drain stage, let's say you have a source follower. That is, you are applying your input at the gate, you have your output at the source. And let's say you have some kind of a DC biasing current source on top. So and if your output is here, so let's say this is my output, this is my input. What is going to be my output impedance in this case? The output impedance, looking down, I'll see this RS resistance, whatever resistance that is. Looking up, I'll see the source of the transistor which have been used as a source follower or a common drain transistor or amplifier. So what is the resistance looking into the source of an amplifier? 1 upon GM. Right? We know this from our earlier discussions for single stage amplifiers, that R out is going to be 1 upon GM if I have a source follower stage, because in that case, I'm looking, my output is at the source terminal. And the resistance looking into the source terminal of an op-amp or of a transistor is going to be 1 upon GM. Right? Now, 1 upon GM is much smaller than RO. Again, you have solved your homework 6, solved your homework 7. You know that 1 upon GM is going to be much smaller than your RO. So this is much better as compared to the scenario we had earlier, where we had RO as our output resistance. Having 1 upon GM means my output resistance is significantly lower. Now you can say that I am going to have, let's say, as large as GM as I can. Right? Let's say I increase my GM as much as possible. So my R out reduces as much as possible. And in that case, you can have an output impedance which is very close to zero. So that is possible to do. With the previous structure, it was not even possible to do. RO2 parallel with RO4, that was always going to be very large. Now that I have 1 upon GM, it's possible to make GM very large. And in that case, my R out is going to be a small number. Of course, it will not be 0, but that is the reason why you have non-ideality in op-amps, right? When you solve homework 2 and homework 3, we assume that there is an output resistance for the op-amp. Why is there an output resistance of the op-amp? Because you have to have something real at the output of the op-amp. And the best that you can do is basically the source follower, which give you the output resistance of 1 upon GM, which could be a kilo ohm, or maybe 500 ohms, or maybe 100 ohms if you're really burning a lot of power and increasing your GM. But it will never be 0. So that's the source, or that's the origin of the non-ideality, that your op-amp does not have a 0 output impedance, but at least it should have a low output impedance. So this is one choice for my op-amp, that I have a differential amplifier with a current source load first. So my gain would be GM1 multiplied with R1 in parallel with R3. And remember that when I had current source loads, which is over here, when I had current source load, I had two outputs. I had two inputs and two outputs. And my gain is basically the input transistor's GM multiplied with either my RO1 parallel with RO3 or my RO2 parallel with RO4. So both of them are same because my left side branch and right side branch are symmetrical. When I have diffamp with current mirror load, then my left side branch and right side branch are not symmetrical. My left side branch has this diode connected transistor here. My right side branch has a common source, or basically that the mirrored load over here. So they are not exactly symmetrical, but in terms of DC, you can assume that they are symmetrical. In terms of AC, they are not symmetrical. And that is the reason why in terms of AC, you get the subtraction of those AC currents at the output terminal, and you have a single output terminal. The gain is equal to, again, input transistors GM multiplied with the output nodes RO, which is RO2 in parallel with RO4. So my first stage could be differential amplified with current source load. So it has two inputs and two outputs. Then I can have another stage of diffamp with current mirrored load, two inputs and one output. Then I can have a source follow. So from the first stage, let's say I have a gain of 20. From the second stage, again, let's say I have a gain of 20. And the third stage, which is source follower, the gain should be GMRS divided by 1 plus GMRS. And GMRS, if it is much larger than 1, then this entire quantity is almost equal to 1. So you can have a gain of, let's say, 400, which is not bad. Right? It's not infinity, but it's not very close to 1 or 10 either. And you can have another stage. Let's say you connect another stage after this. Maybe you have 3 gains stated. So maybe you will have a gain of 20 multiplied with 20 multiplied with 20. So you can get close to that infinite number. And you can play around with these stages, that maybe you can have the current mirror load first instead of having this current source load stage. But having a current mirror load means that you will have only one output. So you need to have a single-ended amplifier after this. So maybe you'll have a common source stage right after the diffamp with current mirror load. And then you can have a source follower or a common drain stage. You can also have diffamps with cascaded current mirror load. We briefly talked about this. Again, this is a more advanced concept taught in analog IC1, that if you want to increase the gain of the single stage amplifier, you can have a cascaded amplifier. And in that case, you can increase the gain even further. Okay. So remember that in your homework 8 and also in your exam, the final exam, you will be asked to solve some sort of a problem related to the op-amp design. Right? And of course, when you solve homework 8, you'll get a very good idea about how to solve that. Okay, so this proof we have already seen, that this is basically the proof of the gain being equal to GM1 multiplied with RO2 in parallel with RO4. And we have seen in the intuitive approach that at the output terminal, you already get the subtraction of the AC current inherently. All right. So if you want to have this example op-amp architecture, that you want to have a diffamp with current mirror load, followed by a common source amplifier, followed by the source follower. I can have gain of GM multiplied with RO2 parallel RO4 from the first stage, which is the diffamp with current mirror load. And that gain is, let's say, 20. My common source amplifier, that can again maybe giving me a gain of 20. And the last stage giving me a gain of 1. So my gain is almost equal to 400, which is large. Let's say I considered it as infinite. And I have infinite input impedance. I have 1 upon GM as my output impedance, because my source follower has a output impedance of 1 upon GM. That's my R out at the source follower. So my output impedance can also be very low. Now, should I still call this a op-amp or should I not? So if I have a diff amp with current meter load followed by common source, followed by source follower, should I call this an op-amp? And because I have asked this question, you can already guess that the answer is no, that we cannot still call it an op-amp. But why is that? The reason is that we have too many poles in the design. What does poles mean? That while you are solving, let's say, your homework 2 and homework 3, you know that if you have a RC, if you have a resistance in series followed by a capacitance in parallel, that becomes a low-pass filter. And the pole for corresponding to this low-pass filter, so if I draw the frequency response of it, my x-axis is frequency, y-axis is amplitude. After a pole frequency of 1 upon RC, or basically 1 upon 2 pi RC, if you consider it as linear frequency, not the angular frequency, that after that particular pole frequency, the signal will drop. On the other hand, if I had a capacitance in the series path and then a resistance in the parallel path to ground, that works as a high-pass filter. Again, something that you have seen in your homework number 3, that if this is F, and again, this is amplitude, then my pole frequency is again 1 over 2 pi times RC, whatever value of that resistance and capacitance is. Now, why am I saying that we have too many poles now? Whenever you have a circuit, whenever you have this circuit, you have the output impedance. You calculated output impedance for diff amp with current meter load, right? So you know that this will have an output impedance. And this will also have a parasitic capacitance. In your homework number 6, you have seen that every node has a parasitic capacitance. So there would be a resistance in series, and then there is a capacitance going to ground. Similarly, here, looking into this black box, you'll have a resistance, and then you'll have a capacitance going to ground. Similarly, same thing happened at this as well. So you just have too many poles, right? You just have too many RC circuits. You do not have a single pole system. When you talked about op-amps in the very beginning, remember that we said that we are going to have these op-amps, we are going to have a frequency response of the op-amp, we'll have a pole, and then the amplitude will drop at 20 dB per decade. So this slope is going to be minus 20 dB per decade, which also means that if I increase my frequency by 10 times, my amplitude is going to reduce by 10 times. And there should be a one-to-one correspondence, one-to-one relation. For that to happen, I need to have only one pole. If I have multiple poles, if I have 2 poles over here, then this slope is going to be minus 40 dB per decade. And if I increase my frequency by 10 times, my amplitude will reduce by 100 times. If I have 3 poles at the same point, my slope is going to be minus 60 dB per decade. And if I increase my frequency by 10 times, my amplitude is going to reduce by 1,000 times. That is not an ideal op-amp, what an ideal op-amp should look like. Because for an ideal op-amp, you need to have this gain bandwidth product. So your gain was here, and the bandwidth was this pole location. The gain bandwidth product needs to be equal to the gain crossover frequency, which is over here. That as if the gain reduces more and more, when does the gain become equal to 1? So let's say the x-axis represents the gain becoming 1. This is the gain crossover frequency. And if your gain reduces by 10 times as your frequency increases by 10 times, the gain bandwidth product will be equal to the gain crossover frequency, which is the case for an ideal op-amp. But if you have a 40 dB per decade slope, or if you have a 60 dB per decade slope, your gain crossover frequency will be much lower than the gain bandwidth product, which is not the property of an ideal op-amp. The ideal op-amp should have only one pole, and that is not what we see in this circuit. We have too many poles, one at the input, one at the first stage of the output, second stage output, source follower output. And when we analyze op-amps, we always assume that they are single pole systems. So there is a disconnect, and we do not yet have our first op-amp. So let's stop here today. And in the next lecture, we'll take a look at how do we make sure that we have a single pole op-amp, and then we'll take a look at the example problem.